Hey kids!
Hey,
Hey,
teacher.
There we go. Very on cue. All right. So let's see where we left off last time.
Oh shit, Antonio.
Oh, there we go.
Oh, that's that was me debugging your stuff. Hold on. I gotta revert my code. Shit. This is where usually I would just restart the recording, but you know what? We're doing it. We're keeping it in.
Yeah.
Oh shit, Antonio. Behind you, you're being attacked. There's a furball.
What the hell?
Oops.
I don't have any furballs at home. I might be getting invaded.
Okay. Maybe now? Ah, there we go. Okay, cool. So this is where we left off last time. So we made the model view projection matrices.
Are you sharing your screen?
No, I'm not sharing this. God damn it. There we go. There we go. Okay. You didn't see my fumbling.
Oh my god.
So we made a we made the model view projection matrices. So we have the model, which is how the quad is oriented in space or in the world. So we had like the standing upright boy, and then we have the laying floor boy. And those are two different model matrices. Then we had the projection matrix, which was transforming depth in the world into, actual perspective magic. So stuff that's further away actually became smaller. So that was the projection matrix. And also did the aspect ratio of the window. Oh, I almost closed it. There we go. It also did aspect ratio of the window. So that's being handled. So that's nice. And then we did the view matrix, which is how the camera is aligned in the world. So we can have the camera spin around here and move up and down. So that's nice. And what's important to note here is that view and projection are the same for every draw call so far. And most likely, when you make your game, you want the camera and the projection to be the same for every single draw call in the world, right? You don't want like one object to have a different camera angle in the middle of the scene or something, or like one object is orthographic while the rest is perspective. So usually you have a view projection that you calculate once, and then you pass that into every other draw call to make sure that those have the same view projection. And then the model matrix is the one you actually change in between draw calls to make them, be in different places and be different sizes. Thoughts? Nothing? Okay, cool. All right, so I'm gonna guess then that this is crystal clear, and there's no weirdness about that. So the way you usually do this when you set up shaders, right now we have it in one uniform. We did like the U model uniform, and there we just put everything in that, every matrix multiplied together. But since we want projection and view to sort of stay the same for every draw call, it makes sense to split them up into separate uniforms. So we have one uniform for view projection that we set only once, and then we have the other U model uniform that we actually swap around in between every draw call. So I'm gonna do that. I'm gonna go into test vert, our vertex shader, and I'm gonna make another uniform here that's a matrix, and it's gonna be called U view projection. So view projection means it's the view and projection matrix multiplied together. You can also, if you're very stingent, you can split view and projection into their own uniforms if you want to, but I usually keep them together. I sometimes also call it like the camera the camera matrix, because it's I don't know, it's usually what you set in the camera. Hold on. All right. So let's set it then. So here where we get the U model uniform, I'm also gonna get the U view projection uniform. By the way, does everyone feel like they can follow along at home? Or is there someone who feels like they are like missing the code to follow along?
You mean like for now?
Yeah.
Yeah, I'm missing like some parts, so I cannot follow along.
Well, you can, if you want to, you can download the code from Canvas, because the code for the last lesson before this is up there, so you can download that if you want to use to follow along. If you want to, it's not mandatory.
Thank you.
All right, so we're getting the U view projection uniform, and now let's set it as well. So I'm gonna, in here where we set the U model, instead of hard coding everything into the model matrix, I'm gonna remove this projection times view. I'm still gonna set that, instead gonna set that in the uniform matrix for FV U view projection. Right, so let's make it view projection matrix is equal to projection, oops, times view, like so. I'm gonna actually do that up here. So here's where we calculate the view projection for this scene. My mic crap code only stretches to lesson 12. Oh no. Hold on, I'll send it to you. Oops. There we go. I uploaded the code to live lecture channel. So I'll upload, there we go. So now I'm uploading this view projection matrix. So I split that up from the model matrix here, this calculation we did here. I took away the view projection here in the beginning and instead made a new matrix up here that is only the projection times view. And then I'm uploading that to the view projection uniform. And what's nice about this is that I only need to do it once. We have two draw calls, and I can remove it here as well, because here we also had to do like the, okay, projection times view times translation, blah, 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 blah. We don't need to do it here either. So we only need to do it once, upload the view projection once, and then for the rest of the draw calls, we only need to upload the model matrix. Because that's the only thing that's actually changing. Okay, so this looks great. So that clearly worked. Can someone tell me why this didn't work?
Have you used the projection matrix in the vertex shader?
No, that's why it doesn't work. I didn't actually use the view projection in the shader. Good call. So let's go do that. So go into the vertex shader here. So we defined the uniform, so that worked, but we didn't actually use it in when calculating the final vertex position. So I will just lock that on in the beginning there. So now in the vertex shader, we're doing what before we did, you know, in the main function in the while loop, where we, you know, manually did, you know, projection times view times all the other stuff. Now we are doing that in the shader, having split them up. So there we go. Now we're back to what we had before, but with two separate uniforms. How does that feel? What are you feeling in your tummies right now? Is it dread? Happiness?
I think I missed something in your code.
Oh, yeah? I'll go back. It is a little bit messy. Did you all get the results? This result of seeing this?
Okay, it's working now.
Okay.
Yeah, I'm good.
Alright, cool. As always, just like interrupt me whenever you have questions or problems or anything. Like it's supposed to be a workshop, not a me talkie. Cool. Okay. So now we have that. So let's try to do some manual camera control then. See what happens then. So how will we do that? Let's do it the easy way first. Let's do that first, and then we might do it a little bit more properly. So I will make a let's make a vector. We know how to use vectors. I'll do a camera position, and I'll set that to 3 by default. So that's going to be our camera position that we want to change using the arrow keys or WASD or something. Friktino. Friktino, hey! Friction. Excuse me. So now we want to actually move the position then using the arrow keys. So we'll check like GLFW get key. Let's do that. So let's see. Let's return the last reported state of a keyboard key for a specified window. So this will give us if it's pressed or if it's, I think, repeats. I actually don't know. I think it only returns. Why am I like speculating? Let's just go to the let's just go to the documentation, shall we? Get key. Let's check it out what it does. There it is. Okay, it only returns press or release, so it will only return if it's down or if it's up. So I will check then key A, so that's gonna be left. So if I hit A on the keyboard, I want to go left. I also need to specify the window. So if GLFW get key window GFKA is equal to GLFW press, then camera position X is minus equal to, I don't know how fast we want to go. Let's just do 1. Yeah, so we want to go pretty slowly. Excuse me, I just need to blow my nose. Excuse me. I'm so stuffy. Okay. So now we're changing. Now we have a camera position and we're changing it. So now let's put that into our view, our look at creation here. Because remember, the first parameter of look at was called I. There we go, I captain. So that's gonna be where the camera is located. So instead of hard coding it or using like a sine cosine function or something, I'm just gonna put in camera position here. Okay, so let's see what happens. Okay, so that's what we expect. So the camera is positioned at, 003, so that's out of the screen, because positive Z is by default out of the screen. so it's 3 units out, which means we're stepping 3 units away from the boy. And if I hit A now, what's gonna happen? Can someone predict what's gonna happen?
Fly away.
What do you mean, why?
Fly away.
Oh, fly away. Okay.
Yeah.
I mean, what are we gonna see though? It's a bit of a trick question. Are we gonna see the thing move to the right?
Think so, because we're not updating the camera position.
Well, we should be updating the camera position here. But remember the second parameters of look at. What is gonna happen? Are we gonna look straight forward? Or is it gonna like fly off to the right and then we're not gonna see it anymore? Or what's gonna happen? Alright, let's try it. So if I hit A. Oh. Let's try it again. Alright, so I'm definitely moving to the left, but I'm keeping track of him like I have him in my eye. I can never let this man out of my sight. Why is that? Do you guys remember? What does the look at function do?
Because we're looking at the that position where the man is on.
Yes, exactly. The second parameter of the look at function is center. So the look at sets a position and then sets what we're looking at. What's going to be at the center of our view. It does not specify a forward vector or anything like that. It just specifies where to look. So that's why, even though we're moving away, we still have him, you know, in the middle of the screen. And actually, we're moving pretty fast, right? I would say we're moving pretty fast. Like, if I hold A, I have to release it pretty quickly to not, like, you know, go way too far away. And I can actually probably make it even worse if I do, let's see, GLFW, disable G-Sync, or V-Sync. Here. Oh, I have to call GLFW swap int. Is that a thing? I want to disable VSync to make it go.
Yeah, it's swap in interval 0.
Swap. Oh, there it is. Okay, so, cool. So now I should probably. It should be even worse. So if I hit A now, yeah, I don't even see a single frame almost of him actually being on screen. As soon as I hit the A, he's just gone. So it's not important that I did VSync. The VSync thing is to up my frame rate, because by default VSync is on, which means that the frame is going to be sort of capped at 60 or around what your refresh rate of your monitor is. So when I turn VSync off, that means it can just run as fast as it possibly can. It's just going to pump out frames. You know, it's probably going to be thousands of frames per second. But okay, can someone tell me, why are we just flying away? Why is it going so fast?
Because we have a very much frames.
We have very much frame. Okay, what does that matter?
We haven't calculated our stuff with the delta time, so when we have 1,000 frames and we move 1 unit each, it's going to move 1,000 units in that 1 second.
Exactly. So now we're gonna move 1 unit to the left every frame when we hold left, which means that, you know, if we have 1,000 frames per second, we're gonna move 1,000 units per second. And, you know, if we have a slow frame rate like I had before, it might have been like kind of manageable. If we're around 60, then it would be like, okay, we move around 60 frames per second, or around 60 units per second. But still, it's gonna be relying on the frame rate for how fast we're going. And do you guys know the word for this? What is this like phenomenon called in game programming? It's something called frame rate dependent. So this code here is frame rate dependent, and what you're looking for as a game developer most often is something called frame rate independent movement, which means we want our movement to be consistent for every type of frame rate you can have. So, you know, if I'm running at 1000 and you're running at 60 frames per second, we want to see the same thing. So this right now is frame rate dependent, and this is important. I want to really hammer home. This has nothing to do with 3D development, but I have people come into Hazelight for an interview and not known about delta time and not known about frame rate dependency and independency, and we have rejected them based on that they don't know to multiply by delta time. So I just want to make sure that this is hammered home. This is very important in game development. Because very nasty bugs can come out of not having frame rate independent code. So yeah, we don't want to move 1 unit per frame. We want to move 1 unit per second. That's sort of the unit we want to work with. If we're frame rate independent, we want to work with per second units. So I want to move 1 frame per second, 1 unit per second, and for that I'm gonna need delta time. So I'm gonna record what our last time is. So let's do glfw get time, I think. Void. Okay, yeah, cool. That's a double. Last time. And let's check out the documentation for this. What does it say? glfw double. Okay. So returns the current value in seconds or 0 if an error occurred. Cool. And here's an important note here. The resolution of the timer is system dependent, but it's usually on an order of few micro or nanoseconds. And this is important because if we're gonna get okay, what was the time last frame versus this frame? If we're 1000 frames per second, if that's 1 millisecond accuracy, that's way too little. Like 1 frame will be microseconds. So if this function was not micro or nanosecond resolution, then we could not use this because it would be too inaccurate for us. So that's a good thing. So I was like, okay, this is what we want to use then. So this is going to be last time in seconds. And then the first thing I'm going to do then in our while loop here is calculate delta time. So I'll do double time is equal to glfw get time. And then I'll set the delta to be time minus last time. Because that's the definition of delta time, right? What is this time it took from the beginning of last frame to the beginning of this frame? What is that duration? So if I keep a track of what the last time was, at the beginning of this frame, I can just compare it to what it was the last frame. Alright, so the time now versus the time last frame. And the difference there is going to be how much time did it take to actually get to this point. And then I'm going to save that as the last time. And the next frame I'm going to compare, the next time. And then I'm going to compare the next time. And then so on. Taking one step at a time. Hey David, is that drumsticks? It's a drummer? It's a ruler.
It's a ruler.
Damn, he's the ruler of your class. Alright. So I'm gonna compare time to last time, and then I'm gonna save last time as time. And now I have this delta. So now if I go into a 1 here, I'm gonna multiply it by delta. And maybe I should call it delta time actually, that's more proper. Oh, bye-bye. It's a double. Okay, fuck it, float. Float is good enough. This is the problem with templates. It can't handle these sort of things easily. Okay, so now if I hit A, let's see what happens. Much more manageable. Much more manageable. Now it seems like we're actually moving one unit every second instead of 1 unit every frame. And let's double check it. If I remove this swap interval here, so we go back to our v-synced 60 FPS, if we are good citizens, we should be moving at roughly the same rate. It looks pretty similar to me. So now we successfully made our code frame rate independent. Very good. Very good, very good, very good, very good. Cool. So let's make the other ones. So I'll make, you know, D and S and W. And I'm actually gonna, instead of doing this, I'm actually gonna make it a little bit easier to read. So I'm just gonna make a vector. Let's see, move camera around. I'm gonna make a variable to save how much we want to move per second of the camera, and then just change that instead, so I don't have to multiply by delta time everywhere. I'm just gonna do camera move. So I'll do camera, whoops, camera move x is minus equals 1. Camera move x is plus equal to 1. Camera move y is... Okay, so if I hit S, I want to go backwards. Okay, so what should I write here? If I want to go backwards with the camera, what should I write?
I think Z plus 1?
Yes, C plus 1. Good one. And if we want to go forwards, then it's said...
-1.
And -1.
-1, exactly. Alright, so now we have sort of the net movement of this frame. I'm actually going to add upwards and downwards as well, just because why not? So I'll do that on space. That's going to be, what's upwards?
-y.
Minus y.
Yeah, y then upwards is -y. Yeah.
Which direction is y in the NDC cube? You guys remember? It's upwards. Y in the NDC cube is upwards. So that means a positive y moves you upwards and a negative y moves you downwards. So unfortunately the right axis but the wrong direction. We're gonna do y plus equals 1. And then if we hit control, you can obviously choose whichever keys you want. I think it's left control. Yeah, there we go. Oops. Then camera move y is minus equal 1. Okay, so now we have the net movement of the camera. Excuse me. So now I'm actually gonna move it. So I'm gonna do camera position plus equals camera move times delta time. So I'm just plussing and adding all together to get the net movement in, you know, per second unit. And then I'm just multiplying it once by delta time. It makes the code a little bit more readable, I think. So let's see. Okay, that looks pretty good. I think... Whoops. Okay, here it actually tells me what's wrong. It tells me the variable camera move is being used without being initialized. So this is sort of a thing in C++. If you just declare something without assigning it a value, so if I, you know, if I just do int my int semicolon, and then, you know, print it, however you want to print, what is this gonna print? Any guess?
42.
42. Okay, any more guesses?
Well, the garbage value.
Yes. Garbage value, yeah. It's just gonna be whatever the memory was before it was initialized. So it's gonna print garbage, or we like to say it's undefined what it's gonna print. So 42, not that wrong. Could be 42 if we're lucky. And same thing with the camera move vector. They do the same thing where they don't initialize anything. If you just declare it like that, so we're gonna do vec3 0 just to make sure it's zeroed out when we define it. There we go. So now let's see if we can move. I can move back and forth like this, and I can move forwards and backwards. Of course, it's not forwards and backwards, in camera space, if you want to talk about that. Like, it's not the camera forward, it's the world forward, world z-axis. So I can move, so I will move around it, and now if I'm behind it, my movement is actually swapped. So if I hit A now, I move to the right instead of to the left, and vice versa. So not the best movement I've ever done, but it's something, it's a start. And what's nice now is that if we want to increase the movement speed, I can just multiply this camera move value. I don't have to go and individually change these ones here, which is what I want to avoid. I can just do times 3, so I'll move 3 units instead of 1 unit. So that's a nice gain we got from splitting it up like this. Now it moves a little bit faster. And I can move up and down as well. Okay, let's address this elephant then. Why is this happening? Down, 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 down. Let's address that real quick and then let's take a break. So, right. So by default, like I said in the last video, by default, OpenGL does not do any sort of depth testing. It doesn't know how far away things are on the screen. Like, it does not prioritize further away objects from closer objects or anything like that by default. So the way you solve this is that if we go into Paint, gonna make it black. The way you solve this, let's draw some pixels. I know you guys love me drawing pixels. I'll just draw a few. Run a little tic-tac-toe grid. Okay, so let's say these are pixels, right? And what's gonna happen is that every time you draw a pixel, that means one pixel is lit up, it's marked what depth it had, in the NDC square, in this NDC cube. So like how deep into the NDC cube was this pixel. So it will keep track of that, not just its position X and Y, but also Z. And it will write that to a separate texture. So let's say, one of these textures on this further away square is like, quite far back in the NDC square. Let's say it's like, 0.8 or something. 0.8. So that's quite deep into it. Actually, it's minus 0.8. Yeah, sorry. Minus 0.8. There we go. Mixed up my forwards and backwards. So quite deep into the NDC square. And, the other ones around are about the same. It's like minus 0.7 or something. And, minus 0.75 and blah, 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 blah. And so on. So we'll fill in that for every pixel that's being drawn. So then when another pixel is being drawn, so let's say, we're drawing the ground here, which is closer. It's closer than the plane on top of the floor. It will look at its C value or Z value in the NDC square and see NDC cube, and see, okay, is this depth, is it bigger than the depth that's in the texture? So we'll compare, this same pixel here and see, like, okay, this pixel on the ground, it has depth 0, so right in the middle of the NDC cube, and it will compare these two numbers to see, okay, this depth that was drawn before, is that bigger or smaller than the new depth we wanna paint? And if it's bigger, that means, okay, this thing is closer in the NDC cube than the previous pixel that was drawn. That is further forward in the NDC cube, and the pixel that was there was further back. So it will say, okay, I should override this. I should be drawn on top. And if it's further away, if it's like, okay, here's a pixel that was minus 0.75 in the NDC cube, and it wants to draw something that's minus 0.9, it will say, okay, this number is smaller, and that means it has been covered. Whatever that was drawn before was further forward, so it should be covered. It should not be drawn. So it will be rejected, and it will keep the previous pixel that was there. And this is called a depth test, all right? Or something called the depth pass. And this is it going over all the pixels and checking their depth value against the previously drawn pixels. And this is by default turned off. Whoops. This is by default turned off in OpenGL. So let's turn it on. I will call GL enable GL depth test. And that will enable this, like checking each pixel and comparing it with the depth value of the previous pixel. Okay, and now we see nothing. Now we see nothing. Why is that? Well, it's because it matters whatever was in this depth texture before. And by default, all of these pixels are being set to as close as possible. So, you know, the minimal possible depth, basically. I think it's actually 0. Whether it's 1 or 0 doesn't really matter. Like, the important part is the theory behind it. But it's being set to the minimal possible depth. So we actually have to clear the depth texture every frame to say, like, you shouldn't be the minimal possible depth, you should be just the max possible depth, and then every pixel will succeed the depth test. So it will not care about whatever was on the depth texture before drawing. It will just be like, I can render because it's the maximum possible depth. So you do that by, in this GL clear, instead of writing GL color buffer bit, we do GL depth buffer bit. And that will actually clear the depth buffer to make sure that we can actually draw stuff to it. The stuff doesn't just automatically fail. And now, okay, so now we can see it, that's good. And if I go below it, ta-da! The floor is now in front of the little man. And if I go above it, the man is in front of the floor. Hooray. We can do this a little bit better though, because this is a bit, and if I look at it, it's actually a bit mask here. So it's 1 bit of a bit mask. And so is color buffer bit, is 1 bit of a bit mask. And that's so you can write it like this. You can do GL color buffer bit or GL color, not color, depth buffer bit. So you can OR them together, and that will clear both the color and the depth buffer bit. So we're gonna do that. So we have one clear call. And now we have sweet, sweet depth, baby. Oh yeah. So yeah, this is called the depth test. Thoughts?
It's eye-opening.
It's like, is this how the world works? Is this why I can cover my face? It's true. Cool. So let's take a 10-minute break. and then we'll continue on with camera movement. So, yeah. At 14:00.
Can you share the code now, because I think I did something. I think I did a lot of things wrong.
You did some poor life choices.
Yes.
I know that feeling. I'll send you the main. Doop 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 doo doo doo. Doop doop doop. Yeah. I'll share it in the live lecture here.
That's a song I haven't heard in a long time.
What song is that
Old
even? Is
song.
that like Spice Girls or something?
No, I don't think that's Spice Girls.
I think it's called I Don't Need Your Love or something like that.
Oh yeah,
Oh, is that
It's
one
so
that's like
far.
I don't need your love because I never felt love before? Is that song?
no. Doopy 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 doop boop boop doopy doop doopy yeah. I don't need your love. Something like that.
I don't think I've ever heard past like the doopy doop part.
I was googling doopy 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 doop.
Doop a doop song. I'm just gonna pause the. Welcome back.
Thank
Thank you, teacher.
Thank you.
Yeah, no worries,
Shit.
dudes. Yeah,
Fucked up.
thank you for saying that unprompted. Okay, so we're gonna do. Let's make it so the camera doesn't actually spin around. All right. Let's make it so the camera only looks forward, so it doesn't turn, because we want to control the turning ourselves. We want to control. Sorry, my fucking dryer is beeping. I gotta go.
No.
Hoppas det här blir med på filmen.
Jag tänkte
Bara en stor
precis.
period.
Vi kan ju säga roliga grejer nu. Som han kommer ha med.
Kan lämna ett
Nej,
meddelande till Emil.
Meddelande från forntiden till framtida lektioner.
Grim vill ha ett kul skämt.
Jag vill ha ett kul skämt.
Mitt go-to-skämt är...
Ja!
Man, I've been putting off doing the laundry for like a week. So
Ja,
now
han är tillbaka.
I'm down to my very last pair of trousers and like socks from like Christmas 2 years ago, and I'm like, so this will just do. All right. So we want to have the camera pointing straight forward. So the way I like to do this is that we keep a yeah, I think the easiest way is just gonna have a forward vector. So we're gonna do camera forward is equal to vec3 0 0 excuse me 0 0 what?
1.
1? What are we
Maybe.
looking at, case?
Negative 1.
There we go, negative 1 I heard, so let's
Right.
do that. So we're gonna look in the negative 0, negative Z direction. So what I'm gonna do is when I'm giving the target, or the center, I should say, what should I put in? I'm gonna guess what I should put in instead of 0 0 0, like the origin. What should I put in instead to keep the rotation constant?
Camera position plus camera forward.
There we go, that's what I wanted. Camera position plus camera forward. Hey man, you should hold the lecture instead of me.
Sure.
Alright, so now if I'm moving around, I'm actually looking the same direction. I'm always looking in the camera forward direction. Very cool. No, of course, if I go behind him, then he's gone. He's gone forever. We're not getting him back. Okay, so how about turning? We want to turn. So we can turn by just changing the forward vector. So the way I'm going to do this, I'm not sure if this is actually the easiest way, but it's the way I'm going to do it. Let's do Have you guys ever worked with Quaternions, by the way?
Yes.
Yes.
Okay,
I-
cool.
I eat Quaternions for breakfast.
From my understanding, they're like if you took two sinus cosinus circles and made them into 3D, you kind of get it.
What?
It kind of feels like it's two circles that you mash together in a 3-dimensional space, and you can like get the exact 3-dimensional rotation from these two mashing these two circles together. I have a hard time explaining it.
Yeah, I don't think I quite follow, but I think you're onto something. But the way we're gonna look at them today is as an axis and an angle, because that's one way to look at Quaternions is an axis and an angle.
I think Euler angles are easier to use there, but I agree. Yes.
Well, yeah, I mean usually with cameras using Euler angles, but I don't want to implement Euler angles right now. The way I'm gonna do this is with Quaternions, because I think in this case they're gonna be easier to use for this. So I will do if glfw key get key. So let's turn with the arrow keys. Yeah, let's do the arrow keys. So I'll do right arrow. Is this key right? It might be this key right. So if we are hitting the right key on the keyboard, I want to turn the camera to the right. So what I'm gonna do, I hope this works. I actually don't know if you can do this easily in GLM. I might be just barking up like a very bad tree here, but let's try. Let's do a Quaternion. Delta quat, and that's gonna be equal to angle axis. There we go, angle axis. So here we're making a Quaternion by defining an axis of rotation and an angle. And if we're yawing the camera, so if we're like sort of pointing like this, turning right, left and right, then we are rotating around the y-axis, right? That's the axis of rotation, right? So if we're yawing the camera, we're rotating around the y-axis. So I will skip angle for now. I'll do that later. But the axis is gonna be vec 3 0 1 0. So just the y-axis. And then angle is how fast we want to rotate. So it's in radians. So I'm just gonna do radians. Let's do 90 degrees per second. So I'll do radians 90 times delta time. Excuse me. So that's our Quaternion, signifying that rotation. So we're rotating 90 degrees per second around the y-axis. And then we're gonna transform our camera forward by that Quaternion. So we'll do camera forward is equal to camera forward times delta quad. No, it's the other way around. Delta quad times camera forward. And hopefully that works in GLM. Okay, great, it does. So multiplying a Quaternion by a vector will rotate that vector by that, by that rotation. So it would rotate the vector around the y-axis by a certain amount of degrees. And let's see what happens. So if I'm in the game and I hit right arrow, okay, so I spin in a different direction. I spin to the left, but I am spinning. So that is what we expected. So we are spinning to the left when I'm hitting right, so I'll use the minus 90 here instead. So now when I hit right, we're actually spinning to the right. Cool. So now I'll do the same for the left. Let's do key left. Let's see what happens. So I made this a positive instead. So now I can look left and right. So now we're like playing Doom or something. Cool. So let's see what will be the easiest way to do this. Let's yeah, let's get the right vector. I think that's gonna be the easiest way to do this. So yeah, let's do movement then. So let's make movement, instead of having movement be along the cardinal directions, or cathedral directions, if you will, we want to have the movement be, when I move forward, I move in the camera's forward direction, right? So if I'm, if I'm standing over here looking to the right, and I hit forward, I expect to go towards the little plane and not forward just along the Z-axis. Like this. Now I'm sort of like half strafing. I want to go forward in the camera's direction. So instead of doing this hard-coded camera move, yeah, let's do here. Instead of having this hard-coded camera move Z plus equals 1, I'm instead just going to do camera move plus equals camera forward. All right. So, oh, that was the S key. Okay, so in S key it would be minus, right? Because when I'm hitting S, I'm moving backwards, so I want to move in the minus camera forward direction. And with the W key, then I want to do plus equals camera forward.
Wait, shouldn't you do rotation first?
I mean, yeah, we could. Yeah, if we want to be super correct, that's true. We want to do the correct the rotation first. So this frame's rotation actually gets taken into consideration. Oh, whoops! I made a mistake. So now, hopefully, when I hit W, I should be moving towards the quad. Hooray, we are. Okay, so now I can move backwards and forwards in camera space. So, the camera's forward is forward, the camera's backwards, backward. So I want to do the same thing with the right and left. All right. So I'm actually thinking if should we do Euler angles? Should we do all-out Quaternions?
Euler.
You guys like Euler?
I think I heard that it's better if you do Eulers because Quaternions have a problem.
It's the other way around.
Yeah.
Euler have
the gimbal lock.
Yeah, you have gimbal lock and Euler angles, but Euler angles, they are very useful. They are easy to work with, especially in editor. Fuck it, let's use the Euler angles, whatever. So so let's forget about this because that was dumb, and I'm dumb. We're gonna do a should we do as a vector or should we do as a flow? Let's do vector. Okay, so we'll do camera rotation. So we're gonna have a camera rotation vector that is, the Euler value. So it will be, I don't know what order it is, but I think it's like pitch, yaw, roll, I think. I don't actually remember. It's probably dependent on OpenGL as well. So we're gonna do something very similar to the movement. I'm gonna make a camera rot, like so. And instead of doing the Quaternion nonsense, I'm instead gonna do. So when we hit the right, then camera rot, I think it's Y, plus equals how fast we want to rotate, so 90, I guess, in radians. And then when we hit left, I want to do minus 90. I don't know if it's going to be plus or minus. Let's just see what happens. I don't think I've ever used your Euler angles in OpenGL. Okay, so now we want to transform the camera forward. So now I don't think we're actually going to transform it. I think we're going to calculate with the camera rotation what the camera forward should be. So instead of what we had before, where we had the forward and we sort of transform it by rotating it, I think we're going to instead calculate from these Euler angles what the forward should be. So we're going to do a Euler angles. What does this do? Oh, okay, that converts Euler angles to a quat, and I think we want quat from... How do you make a quat from Euler angles? OpenGL, GLM Euler to quat. Let's check it out. Wait, is it just angle axis?
I mean, that sounds wrong, but you could do 3 angle axis, I think.
Let's try it. Angle axis. It's just 1. God damn it. Conversion from Euler angles to Quaternion. And the back does not hold. It will not hold. What is that? A Quaternion. Oh, is that how you do it? Quaternion. Oh. I should have looked this up before. This is why I didn't want to do Euler angles, because I don't know exactly how they're implemented in GLM. Let's see here. Angle axis. Well, this one has like X, Y, and Z. But that's wrong. It's wrong. Here, Euler angles. No, that's the other one. I'm sorry, guys. Squad. Okay, fuck it. We're doing it the long way. We're doing it the ugly way. So instead of doing an Euler, instead of there being an Euler angle function, I think they left that out because it's sort of, it is a little bit undefined how exactly you do Euler angles. You know, which order do you do an axis in? So instead, we're gonna make one quaternion for every axis. All right, so we're gonna make one quaternion for the y-axis, one for the x-axis, and one for the z-axis, and then we're just gonna multiply those together so we get the final quaternion out of it. I mean, this is not a math course. This doesn't really matter. So it's okay if this doesn't really stick in your head. So we're gonna do a camera quat. And we're gonna do angle axis. So here we're gonna do camera rot x, and that's gonna be around axis x, like so, times angle axis camera rot y, like 3 0 1 0, times angle axis camera rot z, oops, like 3 0 0 1. Okay, there we go. We did a longhand way of converting Euler angles to quaternions. So now we made one quaternion for every axis, and we multiply those together to get our final quaternion. So this quaternion represents the final rotation. And then to get our camera right out of that, we just do like 3 camera right. Sorry, if to get the camera forward, we'll just do camera quat times the forward vector. The default forward vector. And then we'll do camera right is equal to camera quat times the default right vector. There we go. I was hoping it wasn't gonna be too much math. I'm sorry, but I hope you bear with me at least. We'll do this as smoothly as we can and then move on. So now instead of declaring the forward here and then, you know, updating it every frame, we're just gonna calculate the forward based on our camera rotation, Euler angles here. So we're gonna calculate the forward, and I'm also calculating the right vector. So let's see what happens. Okay, this is gonna be very interesting to see what happens. So when I hit right, oh no. Can you guys tell me why this is happening? When I'm holding right, I'm looking right, or it goes away. And when I'm holding left, it also goes away. Well, this is because I wasn't very good with naming things. Because here I did like camera rot, which was supposed to be like the frame's rotation, the frame's added rotation, and I actually passed that into this Euler Quaternion mess. So it's supposed to be camera rotation, because that's actually our variable up here, our, you know, our camera state. Sort of a mistake by me. It's okay. You can maybe tell that these live lectures are not nearly as polished as my as my recorded ones. So now we're not moving at all because I didn't finish this code where camera rotation is supposed to be, okay, how much do we want to rotate this frame? And then we apply it afterwards like we did with the movement. We calculate, or we sort of gather how much we want to move this frame, and then we apply it afterwards. So I'm going to apply it to the camera rotation here. Plus equals camera rot, and then we're going to have some rotation speed. So I'm actually going to do 1 here instead. And then we define our rotation speed here, and I want the rotation speed to be 90 degrees per second, and then times delta time. So now we're getting out of this. I swear. Now, hopefully, when I hit right, man, if we rotate to the left, I'm gonna scream, "Fuck!" Okay, so we're at least rotating. So, you know, that part worked. It just happened that I mixed up the plus and minuses. But okay, we converted it to Euler angles. It seems to work, so I'm just gonna change this. So when we hold right, we do minus, and then when we hold left, we do plus. Okay. Hopefully the very messy time is over soon. So now, there we go. So now if we hit right and left, we actually look to the right and left.
Yeah, I fell behind during that. It went a bit too fast.
Yeah, I'm sorry about that. Should I copy this code to a live lecture? Let's actually do a 5-minute break so we can sort of catch ourselves up and you know, grab a little breather before we move on. So I will copy this code over to live lecture so you can copy it if you want to. And you know, if this was a mathematics course, like with the last time I held this course, it was actually 3D and mathematics in like the same course. It was like a 5-week double course. And there I went into more details about, you know, how does quaternion multiplication work. We actually spent quite a bit of time on this. And now it's like, since we only have 3 weeks, I want to sort of, you know, get this part over with so we can move on. So it's okay if it doesn't really like register that hard. Maybe you'll get some sort of like, okay, I touched this, but I don't really understand it too much, and that's fine. That's it's it's not the most important part of this course.
Where did you use the camera quad and camera forward and camera right?
Well, here I used the camera quad.
Oh yeah, okay, yeah. But
So-
okay.
So the
And
quad,
the forward and the right.
yeah. So the forward and right here, I calculate those, and I'm currently using forward for moving forwards and backwards.
Right.
And we're gonna be using the right vector to move right and left. So we're gonna be using that shortly. That's why I sort of calculated it now right away.
Okay.
But yeah, you can see camera quaternions. Now we were talking about transforms. I'll say that quaternions is another type of transform. A quaternion is essentially a matrix, but only for rotation. So when I'm multiplying these together, you can see that as, okay, we're doing a rotation around the x-axis. So, you know, we're doing like a pitching. And then I'm combining that with the rotation around the y-axis, which is the yawing. And then the z-axis is the rolling. All right? So I'm combining these into one transform. And that is exactly the same as with matrices. We had, you know, the moving and the rotating and the scaling. We had those as different transforms. And then I combined those into one matrix. And we're doing the same thing here, except we're doing rotation, so we're doing quaternions. So what quaternions are, exactly what the numbers mean, don't worry about it. That's not important. See them as transforms. That's, you know, way more helpful, I think.
I have a bit of an issue.
Okay. You want to share?
Yeah, so nothing happens. Right now, I'm not doing Euler angles, I'm just multiplying quaternions. Camera rotation is a quaternion.
Yeah.
But nothing happens when I'm multiplying this delta quaternion. Shouldn't it just... It should just work, but...
Let's see, camera rots times equals...
So it's defined up here.
Yeah.
And then I'm multiplying the delta quad, just as it was before.
Mm-hmm.
It worked fine when I wrote it as a vector, but now that I'm just multiplying the quaternion into camera rot, it's not doing
Okay, so nothing happens.
anything. Yeah. As I said, worked before with the rotating a vector. Maybe I'm not using. Yeah, I'm using camera forward. Here, yeah.
Mm-hmm.
For look at.
And you don't have the camera forward defined up above the while loop, no?
I have it defined here. Oh, camera forward, no. Camera forward
okay.
is defined here.
So you're calculating it there. Okay, let me see. Okay, so press the right and left keys just to confirm.
Yeah, nothing's happening when I'm doing that.
Nothing's happening.
I'm printed. Oh.
Yeah, I don't know, maybe...
Maybe they don't support it in GLM.
No, I mean, no, that's not a thing. But because you're essentially doing what we're doing, I would, yeah, maybe don't do times equals. Maybe that is not defined in GLM. Try doing like that. Yeah, exactly. Nothing?
Nope.
Okay, let's see again.
I can check up on it later.
No, it's fine. It's a
I'm
workshop.
missing something somewhere.
It's a workshop. The camera is equal to... Delta quad looks okay. Interesting. Okay, let's put a breakpoint when you're calculating camera forward. Motherfucking breakpoint. Okay, so check camera forward. Okay, wait. I know what the problem is. The check camera rot. Yeah, check hover over it, see what it is. Okay, expand it. Yeah, okay, so that's not the identity quaternion. That's a 0 quaternion, which means that everything that's multiplied by a 0 quaternion will be just 0. Yeah, so you gotta make an identity quaternity, quaternity identity quaternion. So you have to do krokodilmunnar. I don't know what that's called. Krokodilmunnar GLM quat. Yeah, this was the way I was planning to do it first, having a quaternion being the state instead of Euler angles, but I thought there might be pitfalls that we would fall into, but yay, hooray, there you go.
Nice, thank you very much.
Yeah, no worries. All right, let's continue then. So I hope you're okay, and I hope you're ready for more, baby. Oh, whoa, whoa. Math coming at you. Excuse me. Okay, so let's do strafing then. So we strafe in the camera's right vector.
Way ahead of you, already did that.
Oh, you asshole. Okay, so we're gonna do. Sorry for calling you an asshole. Okay, so we're gonna do. What am I gonna put in A here? What am I gonna write?
Well, it's camera move plus or minus camera right, I guess.
Yes,
Minus
exactly.
equals.
So we're gonna do minus equals camera right, because we want to move in the negative right direction, which is left. And then here we're gonna do plus equals camera right. So, and let's see what happens.
Quick question. I have to leave. Will this be up on like a video later or?
Yes, this will be a video.
Okay.
So now if I'm strafing right or left, I'm actually moving in the camera's relative right or left. So now if I move around this little boy, you know, I can keep moving with WASD without losing my mind. How very cool. So let's do, you know, because it's 2021, it's not 1993 anymore. Let's actually look up and down as well. So I'm gonna add pitching to this. So which axis is the pitch axis?
That would be X, yes.
Yes, it's the X vector. So I am going to add that here. So we'll do, if I'm hitting up, then I'll decrease X by 1. I don't know if that's right or not. I'm just gonna do it and then see if it's wrong. And then I'll do plus X on the key down. Let's see what happens. If I up or down. Of course I'm wrong. Of course it was the other way around. But it does work at least, so that's good. So I'll just reverse this. Hooray, we can look around. See if I go here. Uh-oh. That's weird. Okay, I'm holding down now, but I'm like looking in a circle. That's kind of weird. Huh. So the pitching is not, I mean, I'm supposed to just look straight up and down, but instead I'm like rolling around. It's not really important exactly why, but can anyone guess why this is happening? It has to do with how we were applying our Euler transforms.
It seems to be like, if I use Unity terms, it seems to be by rolling around the world x-axis instead of the actual camera.
Yeah, exactly. We are rotating. Yeah, I mean, it's not really Kimba lock, but it's kind of. It has to do with how we're ordering our pitch, yaw, and rolls. And this is why I was thinking there probably isn't like a one angle axis to quaternion function, because there are different ways of doing it. There is not one way to convert from Euler angles to quaternion, so that's probably why they don't have one. You can probably see in if you're working in Maya, you can actually specify which type of Euler angle you want to how they are applied, because it matters. Like, it doesn't matter if I yaw first and then pitch, then I'm gonna like roll, or if I pitch first and then yaw, then it's gonna look right. So those two orders will give different results. And right now we can see that we are, because it goes right to left, and we are first rolling, then we're yawing, and then we're pitching. And here's the problem. We're pitching last when we want to pitch in the middle. We want to first roll, then pitch, and then yaw for it to be correct. Whoops. Again, I could go into more detail about this, but I don't think it's super important. This is not the most important thing ever. So now if I look up and down, there we go. Now I have actual up and down movement like I expect. Like I've expected. So not the important part about how quaternions multiply together, not important, but it is important to realize when you're using Euler angles, the order of application matters. The order of rolling, yawing, and pitching matters. Just like, scaling, rotating, and moving, there was a specific order to that as well. Do you guys remember? Where if you, moved or rotated in different orders, you get different results. It's the same thing here. Alright, cool. I think the hard part is over, because now we actually have movement. The scary mathy part is mostly over.
You bind it to mouse axis?
Yeah, that was what I want to do now. So now I want to have it actually be so you can move with the mouse. So if I right click the screen, I want the mouse to be grabbed, and then we can look around using the mouse.
Sounds good.
Sounds hella tight. So I will go into handle mouse event here, which is a convenient function that we have already made. Do you want me to copy this code, by the way? The finished camera rotation code. I see one sad nod in the in the chat, so I'll do it. Live lecture. There it is. Okay. So let's start with capturing the mouse. Let's see if we can get that working. So I want to have it, if you right click, then I want to lock the mouse to the screen and hide it. Alright. So let's check out GLFW documentation, see what we actually can do. Let's see. GLFW lock mouse. Is there a function like that? No. Capture mouse? No. Mouse. Cursor? Cursor setting. I know there is one, but I don't remember the name. Do you guys know? Grim is going crazy, doing some sort of dance move. GLFW lock cursor. Maybe that's what I should search for.
He was throwing stuff at me.
Cursor mode? Cursor disabled. Oh, it looks like something. Cursor hidden. Okay, so what does disable do? If you want to implement mouse-button-based camera controls or other input schemes that require unlimited mouse movements. Amazing. Okay, set the cursor mode to glue GLFW cursor disabled. Tripping over my words here. Okay, so we'll do GLFW set input mode, window, GLFW cursor, GLFW cursor disabled. So we'll just call this then. So if button GLFW mouse button right, so if we hit the right mouse button, then we will GLFW set cursor mode. What was it called? Oh, set input mode. Set input mode, window, GLFW cursor, GLFW, what was it? Cursor disabled. So now if we click the right mouse button on the screen, we should be disabling our cursor, so it should be hidden. See if it works. Ah, there we go. So now I've captured the mouse. So I can move it around how much I want, or as much as I want, but it won't move. But if I release the right mouse button, now it doesn't come back. So it's stuck now. We've fucked ourselves. So that's not good. So let's make sure if you release it, then we should give you the cursor back if we release right mouse button.
Did you say that it locks the mouse, like the position, or just that we can't see it?
That I actually don't know. I'm not sure about what the specific implementation of GLFW is. It might be that it locks it to the boundaries of the screen. Or it might be that it locks it actually in the middle of the screen.
I don't think it locks it in the middle because the kapow gives different coordinates.
Yeah, I saw that as well, but it was giving like crazy coordinates. It was giving like 2,000.
2,000?
Yeah, look. Here's like, it just keeps going. It's like
Wow.
17,000. Obviously, my screen is not that big. So I think that's a fake number. I think that's fake news. I don't think those numbers are actually real. I think the mouse is actually in the middle or by the borders, and it's just incrementing as if there was an unlimited screen area. But yeah, I mean, I'm not completely sure. But let's do this. Let's remove the kapow because we don't need that anymore. And I'm gonna do, if we press the right mouse button, then I'm gonna check, okay, are we pressing, then disable the cursor, otherwise release it. Whoops. Cursor, I think it was normal. Yeah. So if we're pressing right mouse button, then disable the cursor, and if we're releasing it, then set it to normal. So now if I release right mouse button, it should be just coming back. So if I right mouse button, then release, okay, it's back. So I hit right mouse button, and then if I release it, it comes back. Cool. So now we have that. So let's get how much the mouse has moved then every frame, so we can actually rotate the camera using those values. So I will do GLFW get, what is it, cursor plus? Yeah. So I'll do double, I'll do similar to how we did time. I'm just gonna do a double, or let's do a float, because double caused problems last time. I'll do last mouse X and last mouse Y. Oops. Oh my god, okay, they have to be doubles. Dang it. Okay. Annoying. So we're getting the mouse position here as a last mouse X and last mouse Y. And then in the beginning of the frame, we're gonna do calculate delta mouse movement. So we'll do mouse X, mouse Y, and then GLFW get cursor pos, There we go. So now we've got an X and Y, and now we'll get the delta. So now we'll do, mouse delta X. I think that can be a float. I don't want to have it as a double. So we'll do mouse delta X is equal to mouse X minus last mouse X. And mouse delta Y is equal to mouse Y minus last mouse Y. And then we'll set last mouse X to mouse X and last mouse Y. So I'm doing essentially the same thing we did with time. I'm just doing for both X and Y for the mouse. Cool. Does it compile? Yes, it does. Amazing. So let's use this then for camera rotation. So here, instead of doing -1, instead of doing it on key press, I'm actually going to remove this. And I just do... I'll actually do this. I'll do camera rot is equal to vec3, and then it's going to be the x-axis is defined by mouse Y, since that's the pitch. So mouse X is going to be defined by mouse delta Y, and then yawing is going to be defined by mouse delta X. And the C, we don't care about this, it's going to be 0. Okay. So I'm gonna ask you guys this here now. Is this frame rate dependent or is it frame rate independent?
It's frame rate independent.
Why is that?
Because they're using a delta time. It's not dependent on the frame FPS of the game.
Okay.
I think it's wrong.
Oh, is that the other way?
Why is it wrong, David?
Because the mouse is like already time dependent when you move it.
Yes. We're getting the delta movement from last frame to this frame. We're not getting how fast are we moving the mouse per second. We're getting how much did it move since last frame, which is already time frame rate independent. So, you know, if you're running on a 60 machine, that number is just going to be bigger because you had more time to move your mouse from last frame. And if you're running on a 1000 FPS machine, you know, it's going to be smaller because as you're moving your mouse, the numbers is smaller in between each frame. So this mouse delta X is already frame rate independent, which means if we times it by delta time, we're actually squaring it, sort of, since it's already kind of, you can think of it's already multiplied by delta time in a way. So if we multiply it by delta time again, we're gonna get the square. So it's actually turning frame rate dependent again if we multiply it by delta time, because the square of the delta time is not gonna be the same from a low performance machine to a high performance machine. So we're actually done too much delta time, so it becomes frame rate independent again. Frame rate dependent again. So we'll just remove that. So instead, this means for every pixel that we move the mouse, we're gonna rotate 90 degrees. So this is gonna be quite extreme. Let's try it. Yeah, there we go. So if I even move 1 pixel, then I move 90 degrees. So, you know, you can see it sort of flickering because I'm going in snaps of 90 degrees, like I'm playing VR or something. So let's run it down quite a lot. Let's do, let's say we move like 0.2 degrees per pixel Hopefully, maybe that's a little bit more manageable. Ah, there we go. But we've forgotten something. What have we forgotten? Because this doesn't look right. This is not what I wanted.
Need to check if the cursor is disabled, I guess.
Yes, exactly. Because now it's moving all the time when I wanted it to move only when I held right click, right? So I'm just gonna set a bool here. You could probably check the get input mode, but I'll just set a bool. Mouse camera. Sure. So I'll do mouse camera is true, and here I'll do mouse camera is false. And then in the while loop here, where we actually apply the camera rotation, I'll just do if mouse camera. There we go. So let's see. Now nothing happens, but if I hit right click, boom, now I have control. And it's actually exactly opposite. It's when I turn right on the mouse, I'm turning left, and when I move up on the mouse, I'm turning down. So it's exactly opposite. So I'm just gonna minus both of these to get the right pitch and yaw direction here. There we go. Now I'm getting mouse movement like I'm expecting, and I can move up and down like this. And if I let go, then it's fine. We could probably also do like, so you can only WASD if you're holding the mouse if you want to. But he's checking the bool. Cool, we did it. It was a journey, but here we are. We have...
we created Unity.
Yeah, we made Unity. Just a few bells and whistles left, and then we were done. We'll ship it. Okay, so this was probably the most math-heavy section so far. Camera is infamously tedious to do mathematics-wise. You usually have like, one person doing full-time cameras at a company. We certainly have at Hazelight. We have one guy doing only cameras. And it's just because they are very mathematically intensive. Not only stuff like this, but also, transforming cameras from, one to another. How do you blend the cameras from one state to another and stuff like that. But we got through it, and it's fine. And it's okay if this just falls out of your head. That's totally fine. But it is important we have this camera movement for what we're going to do next. We're going to do lighting, and then it's good to be able to move around easily to look at, different angles of our objects and seeing how it behaves everywhere. So that's why I thought it was important to do this, even though it was, quite a chore.
Maybe. Do you think you could, do you have any recommendation for any video that explains more about the camera movement, maybe? If anyone, then it would be great.
I don't think I have one. Most because, you usually don't do this. Like usually in Unity or Unreal, it already has, you just move an actor around and then it's very simple. You just use Euler angles and stuff. The most annoying part here was that we had to actually convert the Euler angles ourselves to get the forward and right vector, which most engines do for yourself. They do that for you. And also, I think it's unfortunate that Quaternions, they are notoriously hard to find good tutorials for some reason. They always seem to go into the nitty-gritty, which I don't think is even important. Like, what's a complex number and how are complex numbers multiplied together. And it's like, this is 4-dimensional object. And I don't even think that matters. Like in our case, it's an axis and an angle, and that's it. And that's all you need to know. And in 99% of cases when using Quaternions in game development, that's all you care about. It's an axis and an angle. So I'm actually a little bit sad about how few tutorials there is, like treating Quaternions like that and treating them like a platform, like a transform. So I don't unfortunately have any nice material.
There's a Quaternion Simulator you can use online. I found that really helpful for when I wanted to figure out some things.
Yeah, it's
Just
like
Google
Quaternion.
it, the first link.
Quaternion. Let's go.
Simulator.
Simulator. Quaternions.online. Oh yeah, here it is. Yeah, okay, so it even has the Euler angles here. And here you see the order here. So they have this problem as well. Where, okay, which direction or which order do you actually multiply the axes is? And they have it specified as all the different orders. So yeah, here you can see the Quaternion as, you know, the raw values. But then if you go into show axis of rotation, here you can see the axis of rotation. You can see that's constant. So this, you know, going around this axis of rotation. And if I, you know, tweak the values and move those around, you can see the axis changing. But yeah, I don't think it's super important to understand Quaternions that much either. They are a very useful tool, but, you know, they're not super widely used either. But they are good to touch every once in a while, just to touch base. Anyways, I think that's going to conclude the workshop for today. I think it was quite a heavy workshop. So I'll do cubes as a video instead. So the next video will be making a cube. And I'm moving around it like this. A
primitive cube?
Yeah, a primitive cube.
Make also a torus.
A torus? Are you crazy?
Yeah, why not? Can we then after that do a tesseract?
That's so hard. Even making a sphere is annoying. Like hard coding a torus.
But it's online. I found this site with all the primitive shape maths.
Yeah. I mean, yeah, you can do them in shaders with like signed distance fields. Then torus isn't too hard. But hard coding, like, you know, even like, you know, we did like a quad, and even that's like annoying to write. Imagine writing this as a torus. that would be rough.
Can't we make a Jabba the Hutt?
Yeah.
Mathematically.
A Jabba the Hutt, yeah, and we'll make a ladybug like those shaded toy. Like, let's actually look at shaded toy. Yeah, that's actually what I did like the previous course. Just look at the fucking like the forests and things being made by just mathematics. Like it's a coffee cup or something.
Oh
but
my
we'll
god.
do distance fields, right?
Yeah, this is all distance fields. So there's no models in this at all. It's only shaders. It's only a fragment shader really. And you know, they have to define all of these shapes mathematically as signed distance fields. So yeah, this is. I usually go on this when I want to feel bad, when I'm like, but my triangle, it looks so good, and then it's just like fucking, whoa, it has music and stuff. It's like looking at this, it's like insane. So yeah, that's the thing. But yeah, anyways, yeah. Any last questions before I call it off?
Are we gonna do signed field functions as well?
I don't think so. Signed field. No, I don't think. I don't think we are. We're mostly gonna look at 3D graphics sort of shaders, whereas, you know, lighting up meshes. Signed distance is mostly used for, you know, if you have a very specific problem that you're trying to solve, like for example, fog, and when you have a mist or something, that is usually done using signed distance if you want to have like a really pretty volumetric fog. And stuff like that, and so like, you know, very special effects. So I don't think we're gonna go through those, unfortunately, even though they are cool, and I would implore you, if you think it's interesting, I definitely check them out. We had a kid last course I did. There was one kid who after my course went like hardcore into signed distance fields and made like, you know, infinite lattices and that you could go run through and stuff, and he had that as his portfolio, and it was very cool. It's a very good portfolio, so he landed a pretty sweet job from that.
Can you put up the latest code as well, the whole project?
Yes, I will do that.
Cool, yo.
As well as the video. All right, cool, guys. yeah, as always, just ping me if you have any questions about anything, and you know, if you want advice on stuff. So, otherwise, I'll see you guys next time. Thank you very much.
Do you want a good...
Thank you too.
Yeah, that's what I was
Thank you,
asking.
teacher.
No problem.
Thank you,
Bye,
teacher.
teacher.
Yeah,
Magister.
no worries, kids. All right, someone.